Helen Keller once said, "There is no better way to thank God for your sight than by giving a helping hand to someone in the dark." Good evening, everyone. We are Manisha, Padmaja, Janvi, and Harshita presenting to you VigNET, an app that helps transform the visual world into an audible experience. More than about 338 million of the world's population suffers from visual impairment. We might wonder how different their everyday experiences are, but normally they're not all that different. They go through the motions of life just like any other ordinary person, but sometimes the simplest things can become difficult to manage, like locating a matching pair of socks or telling a bottle of shampoo apart from that of a conditioner, or even telling which dollar note it is. They need help with these tasks, not hand holding, but just a helping hand, or rather, a helping pair of eyes. Today's technology in education creates an environment where visual impairment doesn't hold people back. With that in mind, our aim for this project was to build an intelligent camera app which provides info about who and what is around you, which is particularly useful for a person with visual impairment. So, what if you had a camera app which you could just hold up your phones, ask a question, and hear information about the world around you, just like asking a friend? For example, what if you had an app through which you could just click a picture of this person and ask the app who the person in the picture was? Well, it is the famous chef Gordon Ramsay, of course, but wouldn't it be great if the app could tell us that? So, we wanted to build an app that does exactly the same. Well, almost exactly. An app that helps answer questions about common objects a user might encounter every day, and a VQA app fits the bill perfectly. So, what is VQA? In general, visual question answering systems attempt to correctly answer questions in natural language regarding the input image. The broader idea of this problem is to design systems that can understand what the components of an image are, similar to how humans do, and communicate effectively about the image in the natural language. This is a challenging task since it requires both image as well as language-based models to interact and complement each other perfectly. This system fits a problem perfectly, but to make it more suitable for our requirements, we added a speech to text and text to speech converters that could help make our app cater to all our major requirements to target our main audience. A high level flow of our app is as shown in this figure. Coming to the project workflow, as a part of our POC, we collected data and performed the required pre-processing and stored the data in GCS buckets and also built a baseline model. Then in the prototyping stage, we started with enhancing a baseline model along with building a few APIs and front-end containers and started working on the deployment setup. In the final stage, we were able to build and deploy a proposed VQA app. A rough sketch of what we had in mind with respect to the appearance and functioning of the app looks something like this. The homepage would have space to upload an image and ask the relevant question. After doing so and clicking the submit button, the answer for the same would be given in both text as well as audio format. The solution architecture for our VQA app looks as in the figure. The solution architecture helps in identifying the building blocks of our app. In our case, the process involves the data scientist who builds a model and the user who interacts with the app by uploading images, asking questions, and getting answers. We then have the execution part where the data scientist experiments with different models used, trained in Collab, and tracks their performance. Here, the user interaction with the app is also satisfied using the front-end code, which gives us the results to our users by communicating with the API service that gets the model prediction. The state here shows how the data and models are being managed. We use the GCS bucket to do the same. Coming to the technical architecture, it provides us with a blueprint of the system. This will illustrate to us how every component is connected with each other. The code was written in IDEs, and each component was containerized during the development of the app, and the code was pushed to GitHub when it was changed for source control. Collab notebooks were used for running different models, and they were stored in GCS buckets. Once the development was done, all the container images were pushed to the Google Cloud registry. The app was then deployed by creating a simple compute instance and setting up containers in this VM. In our case, the front-end container and API service container was set up in the VM, which also communicated with the GCS for loading the model weights. Nginx container is a web server used for serving the web app. The user interacts with the developed app. Now, Janvi will be talking about the data and the models.
Thank you. We'll now look at the modeling process for a bit. We use the publicly available VQA dataset due to its larger size as compared with the others. The basic structure of the dataset can be seen on the slide. It has over 120,000 images with at least 3 questions per image, and each question has 10 ground truth answers along with 1 given answer. Now that we've looked at the data, let's see what the models look like. Because VQA requires techniques involving both image recognition and natural language processing, one basic model that could be thought of is by using CNN for image recognition and RNNs for natural language processing. And then combining the results of these 2 models to deliver the answer. We observed that the results of the model, which used RNNs, were not very satisfactory and had to replace the RNNs with LSTMs, which improved the results by a huge factor. So that was our baseline model. To improve the performance a bit more, we decided to build another model, which is Mobilenet and BERT, and it used their pre-trained weights for transfer learning to perform image feature extraction and natural language processing, respectively. And the results of both were combined as shown to get the final answer. This model improved the accuracy of our baseline model by about 30% and gave satisfactory results. But one major disadvantage of this was the performance speed. Now that we have established that using BERT transform of natural language processing makes the app more efficient, we tried to look into something similar. That is when we came across VILT. To overcome the efficiency versus speed problem faced by vision language pre-training models, VILT was introduced in which the pre-processing of visual inputs is drastically simplified to just the same convolution-free manner in which we process the textual inputs. This makes the VILT model up to 10 times faster than any of the previous VLP models. It also has competitive or better downstream task performances, so it totally fits our task. Now, Padmaja will talk a bit about deployment.
Yeah, thanks, Janvi. So now that we have looked at every single component, we have looked at data, we have looked at the models, let's see how all of them have come together and how this entire app is functioning end to end. So our app, we have modularized into 3 major microservices. First is front-end service, which has all the HTML, CSS components. It then talks to the backend, which is API service. It is built using Fast API. And our API service uses the data tracker service, which continuously keeps track of the model which we are experimenting with. Now we have containerized each and every one of these services using Docker while doing the local development. So once the development was done on the local system successfully, we pushed all of this to GCP using Ansible script. So now that we have covered a lot of theoretical aspects of this project, let's dive into the more exciting part of this project. So handing it over to Manisha for the demo.
Thanks, Padmaja. So now it's time for the demo. This is our VigNET app. So as mentioned before, we have integrated it with the VILT model for getting the answers, because that is the best performing model for us. And this app also supports speech to text as well as text to speech. So now let's see how to use this app. So first of all, the user can either take a picture or upload an image. So let me upload an image. Yeah, then the user can either ask a question or type in the question. So let me ask a question here. How many animals are in this image? Yeah. Now let me submit. I hope you guys will be able to hear the sound. Yeah. Let's see what our model will predict.
Answer is 3.
I hope you guys were able to hear the answer. So the model was able to predict that there are 3 animals in this image, and the previous results will be stored here. Let's try out a different image now. Okay, so here I have uploaded a snowman image. Let's see if it's able to say whether, like I'll ask which, okay, let me ask a question. Which festival is this? Yeah. I hope our model be able to say that it's Christmas, not snowman. Let's see.
Answer is Christmas.
Awesome. So yeah, so one final image I want to upload. I want you also to answer what that image is, and let's see who answers it right. Yeah. So let me ask a question. What is this? Okay. Let me submit and see what our model says.
Answer is statue.
Okay, I hope everyone knew the answer. It was Kim Kardashian, but unfortunately, our model was not able to say it's Kim Kardashian. I think our model was not able to keep up with the Kardashians. Yeah. Anyway, so continuing with the presentation, Padmaja will continue with the results and conclusion.
Yeah, so I think the meme over here kind of concludes what I'm about to say. So we trained with 3 different VQA models. The first model that we tried was CNN with LSTM based models, both of which are really heavy models. So when the accuracy was also not that great, so we see the accuracy of 21% with which takes record 300 milliseconds to give the predictions, which is really high. Then we try to make it a little faster by using BERT for our language as our language model. This drastically improved our accuracy to 51%, but the time taken for it was still quite high. So we clearly have a winner. So we came across VILT model, we implemented the paper, which gave us the accuracy of 70%, and it gave the prediction in a record time of just 15 milliseconds. So we clearly have a winner over here, which is VILT. Now that we have looked into all the different aspects of this app, so to conclude this, I'd say that we can do much better with respect to fine-tuning our models further onto a more realistic data set. And instead of using artificially generated VQA data set, we can use more realistic and real-world scenarios. And we can personalize our app further to recognize more context-specific scenarios. So yeah, definitely you'll have to subscribe to the paid version to get the personalized content. That's a different story. But yeah, we can make it happen. So we can actually train our model to read the documents also and answer the question related to the documents, because we tend to do a lot of day-to-day activities involve a lot of documentation tasks. So this would help the visually impaired people in a drastically huge manner. So that's pretty much about our app. So you can scan this QR code to go to our website, and do ensure that you give the audio, you enable the audio settings onto your website for it to work efficiently, or else you can just choose to type in your question. So yeah, that's pretty much from our side. Thank you so much.